Okay, in this video I'm going to introduce you to a new graph that we haven't used yet, and that is the acceleration versus time graph. So this is the acceleration versus time for an object that does not have a constant acceleration. But it's got an acceleration that increases slightly up and then decreases a little bit and then heads down towards an acceleration of 0. So we're going to start by giving you this hint. This video compares to the finding displacement from a velocity time graph. So if you look back at that video, we're going to use a similar technique now to find change in velocity from an acceleration time graph. So let's take two times, let's just call these T1 and T2, where we look at the acceleration at two different points in time. And if we were to say, just looking at the graph, what would be about the average acceleration between these 2 points? What we would say is at time t1, I have an acceleration a1, and at time t2, I have an acceleration a2, and then because it's almost a straight line increasing slope, somewhere in the middle between a1 and a2 would be what we would call a average. The A average between times T1 and T2 because A is changing. Okay, so what I'm going to do now is a trick that I did before in that previous video, and that is I'm going to draw myself a little box between T1 and T2 at A average. And if I found the area of this box, I'd be finding the area of a rectangle where the height of that rectangle was A average and the width was my delta t. So in this case, I'm going to take my equation for area average, which is change in velocity over time, multiply both sides by delta t, and what I get is A average times delta t is equal to my change in velocity. So if I find the area underneath my acceleration time curve, this area of this little box, I'm really looking at the average acceleration between 2 points times the time interval. Now, in order to prove that to you, we need to go back to this idea that does the area of this box match this area under the curve? And remember, we said to prove that we need to use integral calculus, the integral of A of t from t1 to t2. So that's something that you guys will be learning next year as you move on to calculus and how to figure that and how to prove that. But really the area underneath the curve from T1 to T2 is the same as if I found the average between A1 and A2 and boxed that out. It's that same value. So it gives me my change in velocity. So first thing, important thing to remember, that the area between the AT curve and the A-axis, A equals 0 axis, the x-axis there, is equal to the change of velocity of the object between those time intervals. And I can prove it to you further by looking at the units here. So let's just say, for argument's sake, my average acceleration here was a height of 3 meters per second squared, and my delta t was 2 seconds. So when I solved this out, I had 3 meters per second squared times 2 seconds. I get meters per second squared multiplied by seconds. So one of the squared s's in the denominator cancels with this, and I'm left with 6 meters per second, which are my units, standard SI units for velocity. So area under an AT curve from T1 to T2 is the same as the area of the box from T1 to T2 at A average. And when we find that area, we are finding the change in velocity of an object between those two periods of time. If I have a AT curve that's above a equals 0, I'm in the positive velocity territory. So I have a positive acceleration, so I have a positive delta V. If I have an area below the curve, I'm in the negative acceleration territory. Therefore, I'm going to have a negative delta V below A0. And this only tells me how my velocity changes. It doesn't tell me if I'm speeding up or slowing down. In order to know that, I need to know more information about the position that I'm in and the direction that I'm traveling. Not just how my velocity is changing, but what is my velocity absolutely. This just tells me how my velocity is changing. And that's a very important note to make. Okay, let's look at an example problem. Here we have an AT graph for an object that is accelerating with initially a -2 meters per second squared acceleration, and then jumping up to a +3, and then decreasing to 0, decreasing again to further negative, and then holding constant at a negative value. So let's look at finding delta V for from 0 to 3, from 3 to 7, from 7 to 9, and then from overall from 0 to 9. So from 0 to 3 seconds, my A average is -2. My time interval here, my delta T, is 3. So delta V is A average times delta T, which is -2 meters per second squared times 3 seconds. So my change in velocity from 0 to 3 seconds is -6 meters per second. Now from 3 to 7, and that's the area of this graph. From 3 to 7 I have this graph. I go from 3 to 7, my delta T is 4 seconds. My A average is +3 meters per second squared. So A average delta T, +3 meters per second squared times a +4 seconds, which gives me 12 meters per second. Now from 7 to 9, I have to look at this little triangle area. So I got to do the area of a triangle. My delta T is 2 seconds. My A average is still 3, but my area is 1/2 times 3 times 2, so that gives me 3. So I'm just going to write that down, 3 meters per second. And that's a positive change in velocity. Even though the acceleration is decreasing, it's still a positive acceleration. It's just not accelerating as quickly as we go towards 9 seconds. So overall, by how much does my velocity change from time 0 to time 9? I sum up my different areas. So I change -6, then +12, +3, which gives me, let's see, 6, an overall change in velocity of 9 meters per second from 0 to 9 seconds. All right, challenge for you guys. I want you to find delta V for the intervals from 9 to 11, from 11 to 14, and then overall from 9 to 14 seconds. So go ahead and pause the video. Okay, from 9 to 11, it's -4. So we have this area here. -4 times 2 times 1/2, so it's -4. From 11 to 14, we have 3 seconds times -4, so -12, and then overall, we sum them, we have a change in velocity of -16 meters per second. And that's finding change in velocity from an acceleration time graph by taking the area underneath the curve.